Hello students. Yesterday I went to see balanced rock at Jabalpur. There I got an inspiration to make a video on equilibrium. So in today's session I am going to take up precisely I think 3 or 4 problems on equilibrium. But those problems, though they are not very tough, they are rather easy I would say, but they are of slightly different taste than what you see in your normal books. So let us have this session on torque and equilibrium. Torque and equilibrium. So there might be questions which involve the knowledge of calculating torque and how balancing torque can help us solve questions on equilibrium. So here is our first question. Let us see what does it say. The question says a bead of mass small m is threaded on a light rod that is pivoted to a point O on the vertical wall. This is a light rod, very important, very important. I think you need to pay additional attention to this word, light rod. There is a hint for you. There is a light rod, this is a light rod, it has got no mass and one of its end is pivoted to a wall. This rod can of course swing like this about point O. Initially the rod, and there is a bead, एक मोती जैसी चीज है. There is a bead of mass m on the rod and it can slide on the rod freely, right? There is no friction. Initially the rod is held in position with the distance of the bead at a distance x from point O. This is the bead, it is at a distance x from the pivot point O on the wall. The rod is released from this position and it rotates in vertical plane about O. Rod is released and it rotates in vertical plane about point O. Calculate the angle theta that the rod makes with the horizontal at time t after its release. You release the rod and the question is asking after t seconds what will be the angle made by the rod with the horizontal. The rod will come to some position like this. How is theta dependent on time? This particular question may look very odd to you because writing theta as a function of t is something which most of you have not done anytime, isn't it? But actually the question is not that tough. Initial impression of the question is that it is really very tough, but it is not actually very tough if you focus on this keyword. It is a light rod. What does it mean? A light rod cannot apply any normal force on this bead. What am I saying? If this is a massless object, massless particle or very light particle, you cannot apply 100 Newton force on it. Do you understand that? If you apply any finite force on this, its acceleration will become infinity because F by m, m is 0, m is tending to 0. So acceleration will become infinite. Though that is not permissible. Even if suppose just for sake of argument, let me assume that I have a very small piece of paper in my hand and this is almost massless, it is very light, and by some means I am able to apply 100 Newton force on this. What is going to happen? This will have enormous amount of acceleration and very soon this piece of paper will be miles ahead of me. So how am I going to run after this and apply the same force? So practically we cannot apply any net force on a massless object. Similarly, we cannot apply an unbalanced torque on something which is massless, because if there is an unbalanced torque on some massless entity, it will produce infinite or enormous amount of angular acceleration. If this is our rod which is massless and suppose this bead applies a normal reaction on the rod, just assume that this bead applies a normal reaction on the rod. So the hinge point, the hinge, यहाँ पे जो pin लगा है, जो भी कब्जा लगा है, the hinge will also apply some force on the end of the rod. Because the net force on the rod should be 0, it is massless. Therefore, the force applied by the bead will be equal to force applied by the hinge. Then only the net force can become 0. They should be equal and opposite in magnet. They should be equal and opposite, right? But such pair of force will form a couple, a torque. So if these two are forces acting on this rod, it will form a couple. It will produce a torque, and when the torque is not 0, because moment of inertia of the rod is 0, because inertia is 0, torque is not 0. It simply means its angular acceleration is going to be infinite. So this rod will have an infinite angular acceleration, which is meaningless. Therefore, we can conclude that we cannot apply any net unbalanced force on a massless object. Similarly, there cannot be an unbalanced torque on something which has got no inertia. So this rod cannot experience a normal force due to this bead, and similarly the rod is not going to apply, and therefore the rod is not going to apply any normal force on the bead. If the rod is smooth, as I said that rod is smooth, if the rod is smooth and there is no normal force, is it necessary to say that rod is smooth? Is it necessary? No. No, it is not necessary. That's why it is not written in the question, I guess. If there is no normal reaction between the bead and the rod, there is no question of any friction. So that's why whosoever has written the question, he has not written that rod is frictionless. It's not necessary, because if there is no normal reaction, there is no friction. So when the rod, when you release this rod, the bead is experiencing a weight force, but there is no normal reaction, no friction on the bead. So what is going to happen? This particular bead will fall down with acceleration g. It will experience free fall. Don't you see that? The bead is going to experience free fall. Yes, believe it or not. The bead is going to experience free fall. Yes, dear friends, you have to believe this. The bead is going to move vertically down with acceleration g. नहीं समझे तो रुक के सोचो, समझो जरूर. So I have written that massless rod cannot apply a normal force on the bead, and therefore the bead experiences free fall in time t. It falls through a distance which is given by half gt square. If I release this object and it is under free fall, in time t it will fall through a distance that is given by half gt square. So the bead is going to fall through a distance that will be equal to half gt square in time t. The situation will look somewhat like this. The bead has come down here, it has fallen through a distance y. What is this y? Half gt square. Why? Because this bead is falling down continuously with acceleration g. Students, please try to understand this, very important. Now everything is pretty simple mathematics, right? So this tan theta can be written as y upon x. In the question, this x is a given quantity, and bead is falling vertically down with acceleration g. In time t, it has fallen through a distance y, which is given by half gt square. So I am writing tan theta as y upon x. Y upon x, y is gt square by 2 upon x. Are you getting my point? So this is our final answer. The question asks, calculate the angle theta that the rod makes with horizontal at time t after its release. This is the answer, tan inverse of gt square by 2x. I hope you all have understood this question. नहीं समझे? रोको वीडियो, फिर से सोचो, खुद सोचो क्या कहा गया. फिर भी ना समझ में आया तो एक बार फिर से देख लो. Let us move on to the next question. This particular question says, a balance is mounted on a stationary trolley with weight A attached to its one end. This is a balance, a physical balance, like जैसा सब्जी वालों के पास होता है. ये पिवट पॉइंट है और ये बैलेंस का हॉरिजॉन्टल रॉड है. यहाँ पे एक पैन लगा होता है, यहाँ पे एक पैन लगा होता है. दिस इज व्हाट यू सी विथ एनी सब्जी वाला, राइट? So or at any grocery shop. So a balance is mounted on a stationary trolley with weight A attached to one of its end. At one end of the balance there is a weight A attached. The other end of the balance is linked to the floor of the trolley by a spring. This is a spring force constant is K, let us say. The one end of the spring is attached to the floor of the trolley and the other end is attached to the balance. The diagram is slightly misleading, please. This point is exactly here, right? This point is exactly here. या इसको ऐसा मिटा दो, forget about this, ये नहीं है. This length is D and this length is also D. This is what I want you to understand. Okay. The trolley is accelerated to the right and the string holding the weight gets inclined to the vertical. Now the question says this trolley is accelerated to the right. I am applying some force to push this trolley to the right. This trolley is accelerated to the right, it is moving with some acceleration A. Now all of you must be knowing that this pendulum will get deflected. In its equilibrium position, it will stay in a position like this. All of you must be knowing this, okay. The trolley is accelerated to the right and the string holding the weight gets inclined to the vertical. When the weight gets stable and is not swinging, when the weight gets stable after some time due to a resistance etc., it stabilizes and now the trolley is moving with acceleration A and this is how the pendulum is moving. The string remains inclined to the vertical and it moves with the trolley with acceleration A. There is no more any swing. When the weight gets stable and it is not swinging, does the tension in the spring change? Will the tension in the spring change? While reading the question, I somehow said that, okay, this drawing is slightly misleading. Let us assume that this is D and this is D. I said this, but while I was reading the question, I was thinking about it. Is it necessary that this length D and this length D should be equal? Was the original diagram correct? Keep thinking on it. I will answer this at the end of the solution, right? The balance will remain balanced if torque of forces at the two ends about the pivot point is 0. This balance, this physical balance, let us say this point is O, it is pivoted here, right? And it will stay in equilibrium, it will remain balanced if there is no torque acting on this beam, on this bar about point O. If there is no net torque acting on this bar about point O, then this bar will stay horizontal, it will remain in equilibrium. So we say that it remains balanced when it remains horizontal, right? So it will remain like this if there is no torque about this particular point. This is what is being said. Now let us look at this situation. When the trolley is accelerated, this pendulum gets deflected by some angle theta, and we can work out the value of theta. I hope all of you know this. There is a weight force acting on this pendulum bob. This weight is acting, and then there is a tension force acting on it. In the reference frame of the trolley, you can add one pseudo force. If you are looking at this whole situation in the reference frame of the ground, then there is no pseudo force. But if there is somebody in the reference frame of the trolley, then he or she is allowed to apply Newton's law only after adding one pseudo force. I have already made some video where I discussed about this. Okay, so it depends. You want to work in the reference frame of the ground, it's fine. You want to work in the reference frame of the trolley, it's fine. Right now I am working in the reference frame of the ground, right? So I say that this tension has got two components, T cos theta in vertical direction and T sin theta in horizontal direction. So this T cos theta must be equal to mg because there is no vertical movement of this weight, and this T sin theta is responsible for acceleration of this weight. Why is this weight accelerated? If you ask me why is this trolley accelerated, somebody must be applying some horizontal force on it. But why is this weight accelerated? Then the answer is that this weight is experiencing a tension force which has got an unbalanced horizontal component. So you can write two equations. T cos theta is equal to mg, that is one equation. There is no vertical movement. And T sin theta is responsible for acceleration. So T sin theta, the force, is equal to mass times acceleration. if you wish to calculate the tension in this string, then of course you can square these two equations and add them. So cos square theta plus sin square theta becomes 1, t square becomes mg square plus ma square whole square. So tension becomes equal to this much. So when the trolley was not accelerated, tension in this string was exactly equal to mg. When the position is original position, this tension is equal to mg. When you accelerate the trolley, and if you wish to write the tension in this string, then tension has definitely increased. So this is quite misleading, that many of you must be thinking that if tension has increased, this balance will get inclined like this. No, you need to look at it very carefully. Will it happen? No, no, no. Tension has increased, but what about the torque of the tension force about 0.2? Now let us think of this beam, this bar. Just think of this bar. The string is applying a tension like this, same tension, and this tension has got two components, one horizontal component and the other is vertical component. The horizontal component t cos theta and the vertical, t sin theta, and the vertical component t cos theta. This tension force was acting on this weight. Now just reverse this tension, and the string is pulling this beam, this bar, in this direction with the same tension force. So this tension has got two components, one is horizontal, one is vertical. Now if you look carefully, you will see that this horizontal component of tension will have no torque about 0.2, because this force is passing through 0.2. So when a force passes through, line of action of a force passes through a point, it will have no rotational effect, it will have no torque about that particular point. So if I break this tension force into two components, this component will not produce any rotational effect about 0.2, but this component t sin theta is going to produce rotational effect. Now what is the value of t sin theta? It is mg. What is t sin theta? It is something is wrong, I think. This is t cos theta, I am so sorry. This vertical component is t cos theta, horizontal is t sin theta. So t cos theta is mg. So this force will produce torque about O, which is same as the earlier value. When this car was not accelerated, when this trolley was not accelerated, this tension was equal to mg, and its torque about 0.0 was mg into d. Nothing has changed. Though the string has got deflected, though the value of tension has increased, but the torque of this tension force about 0.0 has not changed. The reason being that vertical component of tension remains same, it is equal to mg. So the torque of this t cos theta about 0.0 is t cos theta into this length BO, which I have written as d. So t cos theta is mg, so mg into BO. So the torque has not changed. This torque has not changed. So why will there be any change over here? Earlier the spring was stretched, it was applying a force kx. This spring force was trying to tilt it this way, whereas this weight force, this tension torque was trying to tilt it this way. The spring force kx was trying to tilt it this way. Because this torque has not changed, why will this torque get disturbed? So actually nothing will change. A spring will not experience any change in extension. The spring will remain as it was. So there will be no change in the spring force, right? Am I right? Am I making sense? So the bar will remain horizontal only. There has been no change actually. There is no change actually. So students, again, stop the video, think for a moment, be careful how you are writing torque about 0.2. This is a very simple question, but I suppose that all of you will pay the necessary attention to understand this. Don't be in a haste to jump on to the next question. Please digest it carefully. Anyway, this is the next question. One thin rod leans on another rod in vertical plane as shown. This diagram shows two rods. This is one rod, this is another rod. Or these two rods have been placed on a horizontal plane like this. One rod is leaning over the other rod. The situation is exactly like this. Okay. This rod is leaning over the other rod. The right rod makes an angle theta with the horizontal floor. This is theta and this is 90 minus theta. And the left rod makes an angle of 90 minus theta, which means this angle is 90 degrees. This is what is being said. The left rod extends infinitesimally beyond the end of the right rod. Question is saying these rods are not placed like this. No, 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 no. This particular left rod is extending slightly beyond the particular rod. That means this is like this. Situation is like this. This is like this. This rod is just kept on this rod like this. It is not like this. No. This rod is slightly extending beyond this, beyond the end of this rod. So situation is like this. I hope you are understanding. It is not like this. It is like this. ये rod इस पे टिका हुआ है ऐसे, right? And the coefficient of friction between the two rods is mu, and there is a friction between two rods, and coefficient of friction is mu, and both the rods or sticks have same mass per unit length. They have identical what I could say, they have uniform cross section, they are made of identical material. So mass per meter length of both the rods or both the sticks is same. Both these sticks have same mass per unit length. The end A and B on the ground are hinged. These two ends are hinged. They are not free. They are hinged. That means these two rods can rotate about the hinge point like this in vertical plane, but they cannot move like this. This is hinged. यहाँ pin लगा है, यहाँ पे भी pin लगा है. Find the minimum value of theta for which the rods do not fall. Find the minimum value of theta for which the pair of rods will remain in equilibrium. This is the question. If you want to give it a try, surely do it. मैं हट जा रहा हूँ, एक बार स्क्रीनशॉट ले लो, क्वेश्चन को ठीक से पढ़ो, 3 बार पढ़ो, करो खुद, ट्राई करो. आओ मैं करता हूँ. I have drawn the free body diagram of these two rods, but I have not shown the hinge forces. I have not shown the hinge forces because I plan to take torque about these 2 points. So I am not going to have any torque of the hinge force about point B or point A if I consider this rod and this rod respectively. So I have not shown the hinge forces right now. Okay, all other forces have been shown. Let us say mass of this rod is m2, so m2g is weight. Let us say rod of mass of this rod is m1, so m1g is weight, and then look at the direction of friction. Look at the direction of friction and be very careful while deciding the direction of the friction. Okay, just by observing this particular rod, you can guess the direction of friction. This rod is in equilibrium. Now the weight force m1g has a tendency to rotate it like this, isn't it? Weight force wants to rotate it like this. So there must be some other force which is trying to rotate it in opposite sense. Which force it can be? The normal reaction will be like this. I hope there is no ambiguity regarding normal reaction, because the question says that these rods are kept like this, isn't it? So the normal reaction because of this rod on this rod will be along the length, and this rod is pushing that rod away, and the normal reaction on the other rod will be like this. So this normal reaction is not going to cause any torque about point A, because line of action of normal reaction passes through A. The mg force is going to tilt it like this. Therefore, the friction has to be in this direction on this rod, so that friction has a torque in opposite direction. If friction on this rod is taken in this direction, then friction and mg both will produce torque in same direction, which can never result in equilibrium. So notice the direction of friction on the two rods. Friction on AC, this rod AC, must produce clockwise torque due to friction to balance the anti-clockwise torque due to m1g. I hope this is clear. Now forces on the two rods are as shown. Of course, I have said that, and we have not shown the hinge forces. That is what is written in here. For rotational equilibrium of this rod AC, we will take torque about point A to be 0 on this rod. On this particular rod, I will rather frame one equation by taking torque about point A to be 0. Now, how will the equation look like? Very simple. This is the equation. This is the friction force F. What is torque of this friction force on this rod? The friction force, line of action of friction is at this distance, AC. AC is this length. So friction force is perpendicular to this rod. Friction, and this AC is the perpendicular distance of this friction force from point A. So F into length AC, this is the torque of friction force. This will be equal to torque of the M1. What is torque of M1G? Now what is M1G? It is weight of this rod. Where is it acting? At the center of this rod. That means if this length is AC, then this midpoint, what should I say? Let me call it as D. This midpoint D, this length AD will be half of AC. So line of action of this force mg is at this much distance from point A. Line of action of this force mg is at this much perpendicular distance from point A. How much is this distance? This distance is AD cos theta. AD cos theta. But this AD is half of AC, right? Half the length of the rod is AD. AD cos theta is this length. This length into mg is torque. So M1G into AC by 2 cos theta. This is torque due to mg. Friction ka torque F into AC. So you cancel AC and AC, this length, and you get friction is equal to M1G by 2 into cos of theta. Okay. This is one important equation that we have got. Next, for rotational equilibrium of the other rod BC, we will consider the torque to be 0 about this point. Now consider this rod. This rod is not going to experience any torque due to this friction force which is passing through point P. It will experience torque due to mg, and then there will be torque due to normal reaction, right? So torque of mg will be equal to torque of normal reaction. This is what you have to write. Now what is torque due to normal reaction? Normal reaction into this length BC. And what is torque due to mg about point B? You can write it in similar way as we did here. This length is half of BC. This length is half of BC, and this length is BC upon 2 cos of this angle. This is 90 minus theta. Cos of 90 minus theta is sin theta. So this length is BC by 2 sin theta into M2G. So we have framed this equation here. Okay, this BC cancels out. Look at it carefully. Normal reaction is equal to M2G by 2 sin theta. So by considering the first rod, we were able to write the friction force, which is equal to M1G by 2 cos theta. And by considering the other rod, we have been able to write the value of normal reaction. But we know that this friction force can never be greater than mu into n. Coefficient of friction is a given quantity in the question. So I'll write friction is less than or equal to mu n. I know that friction is equal to this much. I know that normal reaction is equal to this much. So just by substituting the values of f and n that we have found, we will get this equation. Now what is M1G? What is M1? If mass per meter length of rod is lambda, then lambda into length of the rod is its mass. So here we have written M1 by M2 is less than or equal to mu tan theta. Okay, this 2 has been cancelled out, G has been cancelled out. M1 by M2 is equal to mu tan theta. That's fine. Now M1 is lambda into AC. AC is length of the first rod, and M2 is lambda into BC. BC is length of the second rod, which is less than or equal to mu tan theta. Now what is AC by BC? What is AC by BC? You can work it out yourself. What is AC by BC? AC by BC is nothing but okay, let me go back to the diagram. This is AC, this is BC. What is AC by BC? This angle is theta. So AC upon BC, what is it? This angle is 90 degree. It is cot theta. This is hypotenuse. So AC upon BC is nothing but cot theta. I hope you understand that. So now you can do that substitution. AC by BC is cot theta, which is 1 upon tan theta. Basically lambda goes away. So this is the equation that you get, and next you can write it as tan square theta is greater than or equal to 1 upon mu. Therefore you can write that minimum value of theta is tan theta is greater than or equal to 1 by under root mu. So minimum value of tan theta is 1 by mu. Therefore theta minimum is tan inverse 1 upon root mu. I am so sorry. please do it yourself. So these are the 3 questions, I guess. I don't have any more questions right now. Okay. Maybe in some other video I'll add few more questions to this particular concept. I tried to pick 3 questions which were simple but slightly different from those that you regularly see in your books. So my aim was to illustrate how equilibrium questions can be solved using torque equations. So see you in the next video. Thank you for watching this.